Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 9, our CPS unit. That's not cycles per second, that's curvature, power, and sag. So if you were to throw a rock in a pond, you would notice circular ripples appear. The circles closest to where the rock hit the water are very round, and as you look further away from that spot, the circles appear to get flatter and flatter. If you think a flat circle is an oxymoron, consider what the horizon of the Earth looks like. If you were standing on the beach and looking out at the water, the Earth looks pretty flat, even though we know it's round. The reason for that is the radius of curvature of the Earth is close to 4,000 miles. So the longer the radius of curvature, the flatter the circle. By the way, if you think that an oxymoron is someone who is unfamiliar with OxyClean, that is incorrect. So here's a point source of light producing light waves. The waves closest to the point are very round. As we get further away, they get flatter and flatter. And as we learned in a previous unit, we set 20 feet or 6 meters as the distance for optical infinity. So let's say the radius of curvature of this initial wavefront is r sub 1, and it's measured from A to C, the center of curvature. Now, capital R is what we call the curvature, and its formula is curvature equals 1 over the radius of curvature measured in meters. Big R, the curvature, is measured in a unit called the diopter. So if little r sub 1 is equal to, let's say, -2 centimeters, the curvature of that wavefront equals 1 over minus 0.02 meters, which is a -50 diopters. The flat wave has a radius of infinity, therefore its curvature equals 0 diopters. 1 over infinity is 0. Big U and big U prime are the curvatures of wavefronts that strike an optical surface or come from an optical surface. They're also measured in diopters. So remember, we measure object and image distances. We call them little u and little u prime. They have to be measured in meters in order to establish what big U and big U prime are in diopters. So here's an example. Here's an optical axis. Here's a plus lens. Our object is at M. Our image is at M prime. So our object at M is a distance little u from the lens, measured from the lens to M. That's a negative number, -4 centimeters, and u primes are image distance, measured from left to right. That's, let's say it's 2 centimeters. So big U is equal to 1 over minus 0.04 meters, and it's -25 diopters. And big U prime is 1 over 0.02 meters, and it is equal to 50 diopters. So not only is curvature designated in diopters, but the power of optical surfaces is also designated by the diopter. So any curved optical surface, whether it's a spherical mirror, a spherical refracting surface, or a lens, has its own special power. You can think of these surfaces as being members of the Justice League of Optics. Put little capes on them. So the letter that we use for power is a capital F. And for a spherical mirror, the power equals -2 over R or 1 over F. And the power is in diopters. R is the radius of curvature in meters. It's important to remember. And F is the focal length measured in meters. Now, big U, the incident wavefront's curvature, is equal to 1 over little u, the object distance, and big U prime is the reflected wavefront curvature, and that equals 1 over the image distance, little u prime. And those distances, again, are measured in meters. So the power of a mirror is also equal to big U plus big U prime. For a spherical refracting surface, the power in diopters is equal to n over f, or minus n prime over f prime, or n prime minus n over r. So n is the index of the medium on the left side of the surface. N prime is the index of the medium on the right side of the surface. R is the radius of curvature measured in meters. And F is the primary focal length measured in meters. F prime is the secondary focal length measured in meters. Big U is the curvature of the incident wavefront. It equals n over little u. And big U prime is the curvature of the refracted wavefront, and it equals n prime over little u prime, where again little u is the object distance in meters, and little u prime is the image distance in meters. And the power of a single spherical refracting surface equals the big U prime minus big U. Right, now we'll talk about lenses. So the power of a lens in air is equal to 1 divided by the focal length measured in meters. And that gives you the diopter measurement. The power of a thin lens is equal to the power of the first surface, that's F1, plus the power of the second surface, that's F sub 2. So let's draw a biconvex lens. First vertex is A1, second vertex is A2. We'll place our centers of curvature on the appropriate sides. We'll label M as our object, M prime as our image. So the index of the substance in front of the lens is n sub 1, the index of the lens is n sub 2, and the index of the substance behind the lens is n sub 3. U is defined as A sub 1 to M. U prime is defined as A sub 2 to M prime. R sub 2 is A sub 2 to C sub 2, and R sub 1 is A sub 1 to C sub 1. So the power of the first surface is equal to N2 minus N1 over R1, and the power of the second surface is N3 minus N2 over R2. These formulas simplify if the lens is surrounded by air, which is the usual case. So let's say the lens has the index n, then in that case the first power of the first surface is n minus 1 over R1. Power of the second surface is 1 minus n over R2. The power of the lens is also equal to the U prime, big U prime minus big U. And big U in air is 1 over little u, and big U prime in air is 1 over little u prime. So sag is something that happens to you as you get older. You have less curvature, less power, and more sag. But we're talking about geometric optics. So sag is defined as the distance between the back of a curved optical surface and a chord that you draw from one side to the other. So h is half of that chord length, and r is the radius of curvature of the optical surface. The formula for sag is equal to the radius minus the square root of the radius squared minus half the chord length squared. There is a device called a lens clock. You cannot tell time with it. It is a mechanical device that measures the sag of a curved optical surface and converts it to the power of that surface, because radius is part of the equation and radius is related to power. It is possible to change sag into the power. Now, the lens clock is calibrated for glass with an index of 1.523. If you use the lens clock on a surface that is made of a material with another index, let's say index n, the formula to convert is the true power equals n minus 1 divided by 0.523 times the power that you measured with the lens clock. Now here's a lens clock. The black scale is for plus powers, the red scale is for minus powers. The two pegs on the edges don't move, but the peg in the center does move, and when you press it against the surface, it will tell you the power of that surface. So let's take a meniscus lens here. This is an eyeglass lens. Most eyeglass lenses are meniscus. And we see when we place the lens clock against the front surface that the power is approximately +7. When we hold it against the back surface, we'll look at the red scale, and we see that power is -6. When you add them up, you get the power of the lens equals +1.